Thank you very much for the invitation. I'm sad I can't make it with you in Amsterdam, but this is the next best thing. So thank you, Marco, for setting this up. So I want to give a bit of a different view on, or at least compared to what other people have been talking about in the meeting on containers. And it's maybe a bit less of a positive view initially, but I hope I can wrap up with some, at least some ideas on how to improve things. So first of all, who am I? I did my computer science studies at Ghent University, and then I joined the HPC team there in October 2010. Since then, I've mostly been working on user support issues, and a lot of that time is spent on software installations. And as a part of this, I have become the lead developer of the easybuild tool, which I'll talk a bit more about. So first of all, to come back to the title, do containers really relieve the burden of installing scientific software? In my view, not really. I'll explain what I mean by this. But it's not all bad news. Maybe there's some future perspectives, some things we can work on to improve the current situation. So I want to look at the problem of installing scientific software, and I've heard that this has been coming up in several of the other talks during the meeting. And I'll just give my view on it. Then I'll take a look at the container revolution that's been happening in the last couple of years in the HPC community, and also look at why it happens, or why I think it happens. And then some of the problems I see with the use of containers for scientific software on HPC systems, and then some ideas for things to work on. So first of all, getting scientific software installed, it's a known big issue for basically all HPC cells around the world. So you have this big fancy supercomputer, but you need some software installed on it as well to make use of it. So ideally, you're building this software from source, so you can target the specific architecture of your system. And support teams and researchers and anyone who needs to install the software spend a lot of time on this, and it can be very frustrating. And sometimes only when you have the software installed, you notice that it wasn't really worth the effort. Either the software you've installed isn't doing what you think it did, or it's not working well enough, or maybe you found something else in the meantime that's even better. So you keep moving the problem all the time. In Ghent, I took a look at the user support tickets we get in terms of installation requests. About a quarter of our tickets are somehow related to software installations, but it consumes way more than a quarter of our time. So it's definitely a big issue. And up until recently, there was very little collaboration going on between sites. So, and luckily, this has changed in the last couple of years. So one of the reasons behind this is that the scientific software is written by scientists, by researchers, who are typically not well trained in software engineering. They're not really software developers by training, so they want to get the science done, and the software is kind of a necessary evil for them. This results in basically crazy scientists writing software, so you have all kinds of problems that are quite specific to scientific software in my experience. They don't really know well how to package software or how to use the right build tools or make it easy for other people to get their software installed. So you run into all kinds of problems, and there are several examples of this. One example I like to use is TensorFlow. This is one of the biggest scientific software packages out there right now. It's one of the most popular projects on GitHub, which is already quite big by itself. But if you look at how you install TensorFlow, or at least how you install it from source, it's pretty messy. It provides some scripts where you can install the necessary dependencies for you, which is not necessarily a good thing because you have very little control over how they are installed. And even then, you still have to fill in some gaps like Python or CUDA. It assumes these things are there. So you have to have a good installation of these and with the necessary bells and whistles. It provides a configure script to configure the installation of TensorFlow, but it's not the traditional configure script that people are used to. This is an interactive script, and I think it's written in Python. So you have to give it answers. It asks you questions all the time. And you can do a silent installation of it if you know which environment variables to set. And these are somehow magic because they are not mentioned in the documentation anywhere. So you have to open the script, see what environment variables it checks, and then set the necessary values for it. The real problem with TensorFlow is that it uses Bazel as a build tool. So this is a tool that is coming from inside of Google. And it's really specific to Google. And once it was being used outside of Google, people started noticing that it wasn't really, let's say, well fit to be used in a more general setting. It came to the point where the TensorFlow community was actually contributing back an alternate way of installing TensorFlow from source through CMake. And even CMake by itself is already a bit of an issue. So the fact that people were jumping to CMake because of Bazel is really tells a lot. Bazel is quite weird to use, so it resets the whole environment where it's being run in. So things like Python pod or the location of Intel license files, if they are specified in the environment, or get lost, so you have to somehow inject this back into the Bazel environment. The way you build TensorFlow has the Bazel command is there on the slide, Bazel build config opt, and then you have this double slash TensorFlow yada yada. This double slash is not a typo, that's how Bazel works, so it feels a bit weird. And you have three different options that look very similar. Dash config opt, dash c opt, and dash c opt without the space are three entirely different things. So these are very, very confusing, and to people who are used to Bazel, it's not a huge issue, but if you're not, then you're in a world of pain to figure out how all of this works. So all of this I've been working on things like this for about 7 years in the team, getting all of the software installed. And this led to a talk I did at FOSDEM last year. So if you want to see how bad things are or how bad you can make things, this talk is a good thing to take a look at. So of course, software installation has been done for a very long time on HPC systems, and there are all kinds of tools for it. Package managers, there's tools like Homebrew and the Linux equivalent Linux Brew. There's Portage on Gentoo, there's Package Source that has grown way outside of NetBSD. But none of these are really well suited to scientific software or to supercomputing systems. So typically they have very little support to install software side by side, multiple versions, multiple configurations of the same software. They just assume that you have one single installation of each software, and that's the one you're going to use. And that doesn't work on multi-user HPC systems. They don't really deal too well with the problems you run into with scientific software. They typically don't have good support for compilers other than GCC, let alone MPI or building software for GPUs. And there's a very strong focus on having generically optimized binaries. So binaries you can use on multiple systems, which implies they are not really optimized for your system. I will show you an example benchmark of how bad this can get. So there are exceptions to this in recent years. There's stuff like Conda, which deals with some of these issues, certainly the scientific software part, but it still uses generically optimized binaries to some degree. And easybuild and SPAC built from source. And then Nix and Geeks you can build from source with Nix or Geeks. You can also use binary packages, but there the focus is really on shielding everything in the environment and making sure the installation is fully reproducible. So each of these tools have a different use case. So the container revolution that happened in the last couple of years, so maybe this has already been popped up. I can imagine that Christian was mentioning something like this morning. The containers are really an old idea. They've been around for decades already. And at some point they became really popular in cloud environments, in this hyperscale, Google, Amazon kind of environments. And Docker was a big part of that. So that started pretty much in 2013. In the HPC community, in my experience, it started around 2015. So supercomputing of that year, you saw Docker popping up on the exhibit floor, and people were talking about containers in the HPC community. But in my experience, Docker has never really broken through in the HPC community, and there are some reasons for that. So the security aspect of having a Docker daemon running as root somewhere, and then having all your users talk to this thing that runs as root is kind of a security concern. And this is where Singularity came in. So I saw Dave was talking yesterday about Singularity and the specific features it has for containers in the HPC community. And there's other projects as well, like Charlie Cloud, which was also talked about yesterday. So containers are there now in HPC, and people are using them and finding them very useful with good reason. Now, in my view, why did the container revolution happen? And in my experience, installing scientific software is becoming more complex. It's becoming more and more difficult, more and more tricky to install it correctly or efficiently. A lot of that is due to dependency. So people are more and more picking up each other's work, each other's libraries, and building things on top of other things. So these dependency graphs are getting worse, and in my experience, it's getting worse very fast. We're coming back to the era where there's no longer one single main architecture, x86, but you have GPUs as well, accelerators that you have to optimize your software for, and ARM and Power are coming back into view as well, which also complicates things. And it's actually becoming more important to really target the host system to get good performance, and I'll show an example of that in a bit. On the flip side, scientists don't really have the expertise to deal with this. So they were not trained in software engineering. Most of them have very little experience in releasing software and packaging software or picking the right tool for the job. So sometimes they resort to building their own custom configure scripts or tools like Bazel because they want to maybe solve a problem that has been solved by other tools already. And when they run into compilation or installation problems, it becomes very hard for them to figure out what is wrong, let alone how to fix it. So. And then some of the popular programming languages and applications are not great examples. And I won't name any names here, but I'll put the logos there and you get the idea. And also, people are getting lazy or impatient. Maybe they are forced to be impatient, but that's certainly part of the story as well. So here is an example of a dependency graph of a scientific software package called Chime, which is, I don't know what it does exactly, but it's something in the bioinformatics field. So the part we're interested in is actually Chime itself, which is on the top, and everything else is the stuff we have to deal with to get it working. Some of this is big packages like Python or R. Others are these side libraries, which are by themselves already tricky to install and don't follow a standard installation procedure. So a lot of this there's a lot of pain here that you have to go through before you even get to installing Chime. And then the Python issue, so this is the XKCD cartoon that you may have seen already. So how Python has grown in the scientific community is a good thing in one sense, but it can get very messy as well. So this is a scheme of how things may look like with Python on your personal workstation. So it can get messy quite well. You have Python 2, Python 3, you have 10 different ways of installing Python packages, and all of a sudden it becomes this huge web of things that you can't figure out anymore. And this is why people resort to containers, because there they are shielded off and they have a controlled environment that they can use. So while preparing this talk, I was taking a look at the Singularity website, and I noticed there's a lot of buzzwords. So the graphic there is literally pulled from the Singularity website. It says simple, fast, secure. And there's all of these buzzwords flying around for containers, like mobility of compute is a term that especially the Singularity people like to use. Bring your own environment, so the researcher can define his environment locally and then just bring it to the supercomputer and run it there. They claim they get native performance. I don't fully agree with that, and I'll show you what that means. Reproducibility comes up a lot, and all of these things. Security is not a solved problem. I think that the Charlie Cloud presentation yesterday was showing some of that there's still some concerns there. And then integration with things like GPUs or the resource manager or your home directory on the system is quite important as well. So when you look at these words, everything is nice and shiny and everything works and is solved. Well, no, not really. There's still some problems if you ask me. And in some sense, containers are really a workaround, not a solution. So we're just dancing around in the core problem. And people use containers as an escape hatch. So there's several issues I see. One of them is that a container image is really just a collection of binaries, so stuff that was pre-built by someone, but it's most likely not targeted to your host architecture. So if you have a system that has a certain family of processors, Intel Haswell, or maybe Intel Skylake, if you've done a recent update, your container may not be built for this architecture, and it may be a problem in terms of performance. And a container that was built for an x86 system will just not work on ARM or Power. You have to rebuild it and target this specific instruction set, or it will just not work. You will just get binaries that are totally unusable. When they say native performance, they really mean there's very little overhead that containers introduce. So whether you're running a binary inside or outside of a container, you basically get the same performance. That's very good, and it's actually necessary for HPC. If you wouldn't have this, the HPC community would just flat out ignore containers, and even a couple of % of overhead can already be a problem. But this is not really enough to claim native performance, and I'll explain this a bit more. And then the integration with system resources and services, to some degree, this is a solved issue. You can log into or open up a container and you still see your home directory, you still see your files on the system. That's very useful. There's a good connection with resource managers like Slurm or Torque, where you submit your jobs to on an HPC system. But for other things like GPU and MPI, they're not fully solved. So you do get access to the GPU and you get access to the fast network from within the container. But the libraries that are inside the container have to be in sync to some degree with the host drivers on the system. So you cannot take any container, put it on any system, and assume you will have full access to GPU and MPI. So there has to be some degree of synchronization there, and that's a problem because it means that containers are not fully portable to any system. You have to know some aspect of the system before you can actually run the containers. So the performance aspect is I keep saying, and some people disagree with me, but I keep saying that containers are trading off performance for the mobility of running the container. So they're sacrificing performance, which is holy in the HPC community. So that's a bit of an issue. So I did some benchmarks here this week with a very simple FFTW program, so a fast Fourier transform benchmark that I compiled myself. I built a singularity container for it, and I built it on an Intel Sandy Bridge system, so a quite old 6-year-old system that's in one of our HPC clusters. So the yellow bar is running the container on that Sandy Bridge system. The green bar is running that same container on the Intel Haswell system, so a newer supercomputer we have, and you see about like a 2x speed up just by using different hardware and using the exact same container. That's very good. But then if you look a bit closer, if you rebuild the container for the architecture you're actually running on, you see another 60% speed up. Now, if you just use the existing container you have, you will get a lot of speed up and you'll say, yes, this new system is really doing well. But if you do a little bit more effort, you can get a lot more in terms of performance from the same system. So that means if you're just blindly using the containers you have, you may be losing a lot of performance, and that's an important thing to realize. And the downside here is this only works in one direction. So if you have a container image built for a newer system like Intel Haswell, you cannot use it unless you're very careful. You cannot use it on an Intel Sandy Bridge system because it will have instructions that this processor doesn't know about and will just crash. So you can't have a single container image that works anywhere and you always get full performance, or at least you can, but it's not very easy to build a container like this. So back to some of the concerns. Another issue is that somebody has to puzzle this container image, And ideally, it's the exact thing you want. So it has the software that you need, it has the software versions that you care about. It's fully optimized for your host system. So if you could get your hands on that and somebody else did the work, that would already be very useful. But then at some point, you'll probably want to update to newer versions of the software, and you have this big collection of binaries that you have no control over and no easy way to update. So that can be a bit of an issue. So basically what we're missing, and this is a nice idea, but it's a lot of work to get this right, is a sort of containers on demand service, like a website where you can go, you can just select the software, which versions you want, maybe how they are configured, so which features are enabled in the software, specify what your host system looks like, so what processors does it have, if it doesn't have GPUs, and which generation of GPUs, which versions of the CUDA drivers do you have, or the InfiniBand stack do you have, and then you click go, you wait for a while, you get a container image, and then you can start running full speed. So this is sort of what we want, but it's very, very difficult to build something like this. And there's a lot of details there. So there's other issues as well. I already mentioned security. There's a trust issue as well. So if somebody gives you a container image, it's very hard to figure out what is in there. So maybe you trust this person, and maybe the container image is signed, like the Singularity talk yesterday mentioned. But it still boils down to trust. So somebody is giving you a bunch of binaries, and you have to trust them that there's nothing malicious in there. So in my view, there's a lot of work to be done to make containers really successful in HPC. Not just make them work like they do now, but make them really get everything out of the system, and let people easily update them and so on. So that was the bad news. Some of maybe the good news as well. So there are ideas or ways to improve the current situation. So I'm not saying containers are totally useless. But first of all, people should be aware that it's not all magic and not everything works as well as it could when you use containers. So people should be aware that don't just take a container, run it anywhere, and assume you're getting the best possible value of it. There are some corner cases there and some things to be aware of. What I see now is a lot of chaos in the community. So there's a dozen places where you can get container images, and nobody really knows how they were built or who's behind them. There's no standard way of sharing recipes or anything like this. I haven't seen very good documentation on best practices as well. Like what kind of things do you need to take into account when you build container images, performance, and portability, how does this all work? What do you have to take into account? There are no central, or maybe I should say neutral, repositories where you can share container recipes in an organized way and have them have some kind of proof that they are reproducible and validated. And one thing that's definitely missing, and a spy in the room told me that Christian mentioned this as well this morning, is that some kind of metadata you can capture in the container image, so you can query it later and figure out what kind of system it was built for. That's something very important to me. So you can at least figure out to what degree the container image you're using is capable of running well on your host system. And also, ideally, for building container images, people should use established tools. So not build things from source manually in container recipes, but leverage existing tools. One of these tools, and of course I'm a bit partial here, is easybuild. So easybuild is a tool for installing scientific software on HPC systems. Whenever we can, we prefer building from source, so we can really target the host system. And that's what easybuild does by default, but you can tell it otherwise if you want to. Today it has built-in support for generating Docker or Singularity containers. So you can use easybuild to say, easybuild, build a container for TensorFlow, this version of me, and make sure it's optimized for the host I'm building on. And then in the end, you get a container image that you can move around anywhere quite easily. It has support for a whole bunch of software packages, including nasty things like TensorFlow and OpenFOAM, lots of bioinformatics and chemistry software. We have R installations that include hundreds of additional libraries that are outside of the standard R distribution. Same for Python and Perl. And again, whenever we can, we build from source, so we can target the host system really well. Supports a whole range of compilers and API libraries, in addition to BLAS and LAPACK and FFTW libraries as well. So when you use easybuild, building or installing TensorFlow from source and optimized for your host is a single command. So you run the EB command, you specify which version of TensorFlow you want to use for which Python and using which compilers. You hit enter, and then it runs for maybe about half an hour to build TensorFlow from source. And in the end, you have this module, or if you want to, you can get a container image that contains this TensorFlow version optimized for the host it was running. So just to avoid some misconceptions, easybuild is not a replacement for things like Make or CMake. It just wraps around whatever the software is using to get it installed. It does not replace package managers either. You will still need package managers for things like security-related libraries like OpenSSL or InfiniBand drivers or all of this stuff. So let's say we reuse some things that are installed in the operating system. We don't rebuild everything. It's also not a magic solution. So you will still run into software installation problems. If things do not compile because you're using a newer compiler, that easybuild doesn't solve that for you. But what you do get is you get these recipes included in easybuild. So maybe somebody else already dealt with the compilation issue for you. And when you ask easybuild to install it, it just works because it's a solved problem. I won't go into too much details here, but easybuild is a whole bunch of things. It's a uniform interface, so you use the EB command to install software, and you don't really care whatever installation procedure is being used. You just talk to easybuild, and easybuild knows what to do. That way you can provide a consistent software stack to your users, so things are installed always in the same way, no matter which software package you're installing or who is installing it. It can empower the users themselves, so easybuild doesn't require any admin privileges, so people can use this in their own account on the HPC system. They don't need anything really special. And it can be used to build container images as well. So for the people who want more information about the current support we have in easybuild for container images, can take a look at the link on the slide here at the bottom. So basically what easybuild can do, it can generate a container recipe, either for Singularity or Docker, and it can then leverage the Singularity, for example, to actually build the container image as well. So it is a sudo Singularity build command for you. So you get an image in the end. The image you get was built in turn with easybuild itself. So easybuild will include easybuild commands in the recipe it generates. And building the container image is fully automated. So you just run a single EB command, and in the end, after a bit of waiting, you get the container image. The support we have now is still experimental. It works, and people can use it, but we need a bit more testing, and there are some things that we would like to change or like to improve before we declare this stable. So if this is something you are interested in, definitely reach out to the easybuild community and let us know what works, what doesn't, and what kind of issues you see with the current support. So to wrap up, do containers really solve the issue with installing scientific software? Well, not really. To me, not yet. There are still a bunch of open problems. They're certainly being used a lot right now in HPC, and for good reason. So they help quite a lot with letting researchers getting their work done. But it's not all solved issues. There are a bunch of things that we're maybe overlooking or ignoring right now that should be tackled as well. Like performance or like sharing of recipes that are well written, that are easy to maintain or easy to update. Hopefully that leverage existing tools like easybuild or some of the others I mentioned. And also the tracking of metadata is an important thing that should be tackled in one way or another. That's what I had, and I hope there's still some time for questions.